Hello, my name is Danica Kragic, and together with two of my students, Joanna Mizioni and Petra Poklukar, I'm going to present our ongoing work in the area of robot learning with a focus on perception, interaction, and collaboration. Our scientific work has covered and still covers several areas of classical robotics automation. And it's also looking into how we can make human-robot interaction more natural and equip robots with the ability to learn from interaction and collaboration with humans. Apart from looking into problems such as automating more classical cores, such as, for example, warehouses and building robots for systems like that, we look in particular into problems of physical human-robot interaction, where, for example, robots and humans are collaborative carrying around various types of objects. We'll look into automating interaction with deformable objects, so automating tasks such as folding, and also looking into how we can build interactive scenarios where a robot can serve both as a student and a tutor. So, for example, here we are looking into how to equip robot with the capability to observe human interaction with the dove, a deformable object, and extract the level of knowledge that one can assume human has about executing a task like this, and then the robot providing either a tutoring help while, as I said, at the same time extracting information of the human knowledge. So in order to be able to do that, we do focus very much on the physical interaction tasks, context-rich interaction tasks that come to us humans very naturally. So these are just examples of some of the tasks we are doing on a daily basis, but there are still very few or no robots out there that can perform tasks such as these ones in operant environments. And there are many interesting problems here, apart from the, of course, control aspects and modeling rich contact-based interaction tasks, to also address problems such as learning perceptual cues, representing this in a efficient manner so that the robots can perform some of these tasks in real time. So boiling down on a single slide, why are we interested in dealing with various types of interaction tasks? These are interesting from the control, machine learning, perception, and human-robot interaction perspective. And of course, if we are to deploy robots in human-inhabited environments, there will be lots of interaction with humans apart from automating things that we humans do on a daily basis, which most of the tasks are then context-rich tasks. There are examples or comparisons we can do with contact-free tasks that have also been studied very widely in robotics. But what really makes it interesting in terms of contact-rich tasks is that they have rather complex dynamics and also require, let's say, both the low-level sensory problems or sensory perception problems to be addressed together with task and motion planning aspects. And deal with this given the feedback control, real-time perception and control, and then also the fact that we can use, apart from the classical control analytic methods, also data-driven approaches. And in addition, some of these tasks need to be executed or modeled, even if we don't have access to the direct measurements of some of the complex physical properties, such as, for example, friction, but these need to be extracted through interaction itself. More recently, we have also addressed the problem of advanced interaction with deformable objects such as clothing items. And of course, here we see an additional example of interaction for our future research, which is in the area of assistive dressing. And there are several problems that one needs to address here, from the high dimensional state spaces and control, understanding what are the relevant both global and local type of features one needs to rely on. How do we do this with dual arm robots, and then at the same time also considering that we do this while the human body is potentially also changing its position or pose and posture. And of course, classical control methods won't be sufficient here, so we are looking into how to use adaptive control, model predictive control together with data-driven methods and other and relevant methods from the machine learning community. And for this particular direction of our research, we have also looked into how we can build benchmarks so that we can make it also easier for the community to engage in this type of research. Now, our work in state representation learning then relates to different sub-problems that has to do with defining representations that are task relevant, that can also work on different types of robot embodiments that take into account multisensory data, take into account rigid soft deformable objects, and learn in interaction with these continuously, actively, incrementally, and so on, and also give us the ability to retrieve some of the parameters of these objects or attributes that go just beyond the pure shape. For this, we are relying on combination of analytic and data-driven approaches, and in particular also look into sim-to-real transfer. So I just wanted to give a couple of examples. This is from the NeurIPS data track to be just published. So we looked into how to build advanced environments from basic simulations, where in particular we focus on dynamic tasks with topologically non-trivial deformable objects. And why do we look into this? Because we want to build, again, benchmarks that allow us to study various types of control algorithms together with representation and perception that allows us to do this in real time. So just give you a couple of examples of what types of tasks we integrated into this benchmark. We look into tasks such as putting a tube scarf over the mannequin's head, putting a mask over the ears, putting a backpack with long handles around the mannequin's arms, and so on. And we refer to lots of the work that we have done previously that then has to do with representation learning and integrating various types of insights from logical, geometric, probabilistic ways of representing data in order to be able to address problems such as formation control, cutting of soft vegetables, dealing with physical human-robot interaction, defining control algorithms over high-dimensional spaces, looking into physical interaction with objects, and so on. So this is just a short introduction before two of my students. First, Joanna Mizzioni, who works on developing control algorithms based on learning for, in this particular case, cutting or slicing of vegetables. And she's going to talk a little bit about how we think about what are the relevant sensory feedback for these, how we can do this adaptively. And the second student, Petra Poklukar, who is going to focus solely on the representation learning part and present her recent ICML work and continuation of that in order to be able to understand how to evaluate the learned representations in a better way. So I'm going to give them the word now.
Hello, my name is Joanna Mizzioni, and I'm a PhD student in the Division of Robotics, Perception and Learning in KTH, Sweden. And today I would like to talk about one part of the work we do is manipulation of deformable objects, and more particularly the work we do with robotic wood cutting. So robotic wood cutting is in general a pretty challenging task because it is almost impossible to model its dynamics analytically. And that happens because we have a lot of dynamic continuity, as well as the objects that one typically finds in cutting task are non-homogeneous, which means that depending on what we're cutting, we're going to get a different response. There is huge object variety to take into account. There is a lot of friction, which is notoriously nonlinear, and most of the objects that we use are non-rigid. So a lot of assumptions that we could have made about the interaction dynamics are now immediately violated. The approach we have decided to take in RTL is a data-driven model-based approach. And obviously that means that the first thing that we need to do is to get enough data to fit the model. Now, as is the case in most tasks that involve deformable objects, simulating the interaction is really difficult, and the simulations that are available are not useful enough for us to learn an accurate model of the dynamics. So conceptually, that means that everything we do starts and ends with a robot. Now, unfortunately, that also means that everything we measure and everything we want to use is constrained by our hardware. Different robots, different sensors, different control laws to gather the data will result in a different model for the same task. And as an example of this, I would like to show you what a latent space that we're trying to learn and looks like when we just change one assumption about the control input. So on the left, we see the TSME embedding of a lot of different data sets, that cutting data sets of this object. And here we had made an assumption that the force, the desired force that the system wants to exert, will have an immediate effect on the system. So we'll be able to observe it immediately or reach that force level. And as you can see, gathering data with this results in a not very cohesive latent space with no structure whatsoever. Now, on the right hand, we made a little different assumption, and that was to model the effect of a control input, including a delay. What will happen will not be immediately observable, but after a little bit. And just in making this assumption, we immediately reach a latent space that is much more cohesive, much more well-defined, and obviously easier to learn. And so, yes, we did learn. We did a lot of experiments. We showed that learning on that nice latent space and using some specific training techniques, we can get a model that outperforms baselines. But what was most important, the conclusion that we reached from this work was that it is absolutely possible in a quantum-physics task that we will have similar models when you compare them based on the learning curves that have completely different behaviors when you plug them in online. And that was a big mystery, because when you're just comparing the learning curves and everybody has same or approximately the same training and validation scores, and then some of them, when they act as a model for the controller, leave the controller to instead of behaviors, it gets a little bit dangerous. So then our basic idea was that since interpretability of deep networks is something that is very useful nowadays, we would like to use interpretability to explain our predictions. Unfortunately, when we say interpretability usually means images, because that is the human brain knows. Things are obvious to us and we understand something when we can visualize it. But the problem is that the interaction dynamics are inherently not images. They are velocities, they are forces. Those are not in image format. So that means that we need to build images. And after a bit of deliberation on what are the characteristics of an image that we need to preserve, we concluded that the important parts are that it is two-dimensional, that it's compact, that is visually intuitive to whomever is looking at it, and that it represents the state of the system at that particular point well enough so we can learn from it. And we achieved all those points by introducing what we call Kinodynamic Images, which are basically sequences of measurements that we take during a task execution and then transform them into two-dimensional, compact, intuitive, and useful presentation to learn from. And to give you an example of those, let's go back to the example of cutting. When we are above the object and moving downwards to start the task, there are not going to be any forces. So forces are almost zero, there's some marginal sensor. Control inputs are pretty mild, and then we have a lot of displacement on the axis of motion. Then when we are normally cutting through the object, so we are sawing to break friction along that axis and then move downwards, we have a lot of displacement on those two coupled axes, and of course forces at the component end. And then lastly, let's say that we are now in the case where the object is too stiff for the controller parameters we have chosen, and the knife is stuck. Then that can be observed by just looking at dynamic image and noting that there is no displacement, but instead we have a very high force. So after we got that representation and that's qualified for what we would like to use it, we needed to couple it with an interpretability model to be able to trace what part of that input led to that output. And we do that by using RADCON, which is just an interpretability method for image classification. So basically it answers the question, if the answer of the network is this class, what led to it? And that works very well for our case as well. For example, here you can see the output of a model that was trained to predict if there is going to be motion in some future time, so if we're going to get stuck or not. And the answer of the model is that yes, there is going to be motion, and I'm very sure about it because there is a lot of downward progress on axis Z, and it was right. Now to go back to the beginning and the initial question that we asked, is how is it possible that two models that have the exact same training and validation scores behave so differently? And for this, I'm going to show you this example of those two networks that have been trained with slightly different learning rates, and the only difference in their scores is this one. And so the answer to my question is that they behave so differently because they are looking at different things. The way they reason about their predictions is completely different. For example, I'm going to show you that this network down here pays a lot of attention on the forces on axis X, which is the wrong axis to look at. And just by looking at it and evaluating it this way, we can now tell that when we plug this online with the actual robot, if there is some noise on that axis, it will probably lead to the wrong prediction. Of course, it's not possible to go through every decision when it was made through all the data set and then evaluate it visually, but what you can do is you can aggregate those decisions in general and then see how the features that you have used in your image contribute to the decisions of your networks. For example, here you can see the two networks that we decided previously, that we discussed about previously. For this network, the thing that leads into most false positives is the displacement on Z, as opposed to this network that is the control input in Z. And so depending on the task, depending on the final application, this can help resolve and evaluate if the model is appropriate for this task or not by predicting how its behavior is going to be and what will affect it when it's executing the task on the delivery. And that is all for me. And thank you.
And that was Joanna. And now we're going to move to Petra and show you the work on how to assess various types of representations.
Hi everyone, my name is Petra Buklukar, and today I am going to talk about our work on geometric evaluation of data representations. So one common approach to evaluate the quality of learned data representations is to assess the representations based on their performance on pre-designed downstream tasks. Typically, these pre-designed downstream tasks either rely on labeled data and are used to evaluate the ability of the model to recover labels of raw inputs, or the transferability of the representations to other domains, or in cases where labeled data is scarce or perhaps does not represent the nature of the application, handcrafted downstream tasks are used for evaluation. So for example, in robotics, one can use a very specific robotics task to evaluate data representations, while in reinforcement learning, one can use the performance of the policy. We argue that such evaluation has several limitations. It can be time-consuming to both define and design downstream tasks and to collect the data to perform such evaluation. In some cases, there might be even challenging to define a meaningful downstream task, or on contrary, there can be many potential downstream tasks, and selecting a subset of them could bias the evaluation process. So in our first work, GeomCA, Geometric Evaluation of Data Representations, which was accepted and published at this year's ICML conference, we addressed the problem on how to evaluate the quality of data representations directly. That means without relying on any downstream tasks. So an example of representations that we wish to evaluate is visualized in the example on the left. And in our work, we argue that an evaluation framework should be general. And by that, we mean not only independent of the evaluation task, as we discussed before, but also of the model that generates representations and the dimensionality of the data representations. But we argue that the framework should also be informative. And by that, we mean that it should provide insights both into the global structure of the entire learned representation space, but also of the local areas where potential failures arise. So in our work, we present the Geometric Component Analysis framework, or in short, GeomCA, which is based on the idea to compare topological and geometrical properties of two sets of representations. So in the example on the left, we now have the set of blue representations, which we call the reference representations, R, and a set of orange representations, which we call the evaluation representations, E. And we take a simple approach. We build a graph and we derive the GeomCA scores by analyzing the connected components of the obtained graph. And in particular, we look at two criteria. The first is to look at the diversity of points from both sets in each of the connected components. So in this example on the leftmost component is not diverse in points because it does not contain any blue points, while the components inside the dashed box are diverse in points because they contain both the orange and the blue points. And the second criteria is to look at the diversity of edges among points from each of the sets. And in this example on the left, we visualize edges connecting blue and orange points in gray color, and edges connecting points from one of the sets with the respective color of the set. And now when we look at the diversity of edges, we can see that the connected components marked in solid lines are not diverse in edges because they either contain very few gray edges, like the rightmost component, or like the leftmost component that does not contain any gray edges. While the connected components inside the dash box are diverse in edges because they contain many such gray edges connecting blue and orange points. So our derived GeomCA scores can be used both for global evaluation. One of the examples is, for example, to investigate mode collapses in neural networks. This is what we've done in one of the experiments where we investigated mode collapse in the StyleGAN model trained on the FFHQ dataset. And in this graph below, you can see on x-axis the severity of the mode collapse, and then on the y-axis the result of our scores, which correctly capture the behavior. But they can also be used in local evaluation, for example, to detect outliers or identify points in specific components. which is what we did when we investigated the representation space of a VGG60 model pre-trained on ImageNet. And in this example below, you can see images from the ImageNet dataset that are contained in the same connected component, but are annotated with a different label. So these are shown in red. And in blue, we, on the other hand, show some of the detected outliers. So our GCA framework uses the so-called epsilon proximity graphs. And in an epsilon proximity graph, 2 points are connected by an edge if they are at most epsilon distance apart. So in this example below, you can see on the left-hand side the original points from the reference set and the evaluation set. And then on the right-hand side, you can see the obtained epsilon proximity graph, where now epsilon is estimated from the distances among points in the reference set R. And now in this visualization, you can already see the first limitation of the GeomCA framework, which is that a single value of epsilon does not always capture clusters of different shape and density. So for example, in the top right points, the shape of this cluster is not well captured, while in the bottom part, we obtain many isolated blue points. And now the second limitation of the GeomCA framework is that it does not provide any functionality to evaluate the quality of single query representations. And this is useful in applications with continuous stream of data, where we, for example, want to compare the newly arrived data with some of the previously observed data. And now we address these two limitations in our follow-up work, where we present a new framework called Delaunay Component Analysis, or in short, DCA, which is currently under review. And in this work, we replace these epsilon proximity graphs with natural neighborhood graphs called Delaunay graphs. And an example of a Delaunay graph on the same configuration of R and E points is shown in this visualization below. And you can see that 2 points here in the Delaunay graph are connected by an edge if they are the so-called spatial neighbors. Formally, this is defined through Voronoi cells. So 2 points are connected by an edge if their Voronoi cells intersect. And now we can see in this visualization that the Delaunay graphs naturally capture local changes in the density of the representation space. So we get in this example, we can see that the shape of the top right points is captured very nicely. And on the other hand, on the bottom part, we obtain points that are connected instead of many isolated points. And what is more, we can exploit this natural neighborhood structure and define an evaluation framework to evaluate the quality of a single query representation. And we can do that by simply extending the existing graph with edges connecting the query representation with all the previous representations. And then we can evaluate the graph neighborhood of this representation point in various ways. So for example, we can look at the number or length of the edges in the graph neighborhood of this point, or we can adjust the evaluation based on the application that we're considering. Now, the entire DCA framework consists of the following steps. So first of all, we approximate the Delaunay graph that you can see on this example on the right. Then the next step is to distill the Delaunay graph into connected components. We do that by deploying a hierarchical clustering algorithm, which cuts some of the insignificant edges, as you can see on the example on the right. And then once we obtain the connected components, we can simply apply the previously defined GeomCA scores on top of that. So if you remember, GeomCA scores are consider the diversity of nodes and diversity of edges in each of the connected components. While on the other hand, alternatively, we could also, as I previously explained, extend the graph with a query point, and then evaluate the graph neighborhood of this query representation. So we showed that our DCA scores are more stable and more reliable when the reference set R and evaluation set E contain outliers and components of varying density. And in this visualization shown on the slide, you can see that our scores, which are marked with green rectangles, exhibit both low variance when we slightly perturb the geometric configuration of R and E points. And you can also see that the scores that we obtained are close to the optimal scores, which are shown with the with the horizontal blue and orange lines. And we compare our DCA scores with several benchmark methods, including our previously defined GeomCA. On the other hand, among other experiments, we also show various use cases of the evaluation of the query representations. So, for example, we use this extension to evaluate the quality of individual images generated by a style GAN. And in this picture below, you can see query images that are close to the reference representations R. These are shown on the left. And then on the other hand, you can see on the right, the query images that are far away from the reference set R, and these are shown on the right. And you can see that query images that are close to the reference images are also visually of higher quality. And another example is when we investigate semantic similarity of a representation space in the VGG16 model, pre-trained on ImageNet. And again, in these images below, we show an example of a query point and the corresponding closest reference point. And we identify cases where there's no clear semantic connection between the points, indicating inconsistencies in the VGG16 model. These are shown on the left. And on the other hand, we also observe cases where points exhibit strikingly similar semantic similarity, but are annotated with a different label. And such example is shown on the right. And this indicates some inconsistencies in human labeling. So if you wish to know more about our work on geometric evaluation of data representations, you can contact me, Petra Poklukar. You can visit my website as well. And I encourage you to look at our code for GeomCA, which is publicly available on my GitHub. And you can also stay tuned for the code for the extension, for the DCA extension. Thank you for listening.